Hello, this is Lesson 6, Quadratic Functions in Precalculus, and corresponding to Section 2.1 in the College Algebra textbook. This is Ruth Trigstead, your instructor. Let's go ahead and get started. First of all, we're going to graph the quadratic function f of x equals x minus 3 squared plus 2 by applying transformations to y equals x squared. So this should probably be review for you a little bit at least. I'm sure that in other math classes you've looked at graphs of quadratic functions, which you would know as parabolas. But let's go ahead and take a look at how we would start with y equals x squared, which we have right here. And we're going to do some transformations to the graph of y equals x squared until we end up with f of x equals, whoops, I missed part of that, f of x equals x minus 3 squared plus 2. So the first thing we'll want to do, and we've just been talking about transformations in class, so the first thing we want to do here is we want to look inside to the input to the function, and we have x minus 3 there. That tells us that we're going to move our entire graph of y equals x squared to the right by 3 units, which right here, if we identified what we have at this point, would be the graph of y equals x minus 3 squared. One more step to go. We want to take care of that plus 2 on the end there, and what that does is just moves our current graph up by 2 units. So now we have f of x equals, a graph of f of x equals x minus 3 squared plus 2. Okay, so a couple things, if you remember back when you had this before in Math 1010 or whatever previous math class you studied quadratic functions in, the vertex is an important part of a parabola. The vertex is, in this case, since our graphs all open up, it's going to be the low point on each of these 3 graphs. What is the vertex? In the first graph of y equals x squared, the vertex is 0, 0. The second graph has a vertex of 3, 0. And the third graph of our function f of x has a vertex of 3, 2. Okay, so that's the vertex. What about the axis of symmetry? Well, the axis of symmetry is a vertical line. In this case, we'll actually see other parabolas later on in the course. A vertical line that goes through the vertex. So right here on our last graph here of y equals f of x, I'm sketching a little dashed line where we would have the axis of symmetry. And in this case, the axis of symmetry is the line x equals 3. Okay, so we have a vertex of 3, 2. The axis of symmetry is x equals 3. Let's go on and look at the standard, sometimes called the vertex form of a quadratic function. And that is f of x equals a times x minus h squared plus k. If we can get our quadratic function into this format, it's easier to work with in some ways, particularly when we're graphing, because we can look at this function and we can see right away that the vertex is hk here. The axis of symmetry, as we saw in the last example, we're going to look at the first coordinate of the vertex, and that identifies our axis of symmetry. In this case, it's being x equals h. If a is greater than 0, our parabola is going to open up. So a is the number here in front of the x minus h squared. If a is less than 0, our parabola will open down. And so a is greater than 0, a parabola opening up is going to look like this. And notice that we would have a minimum value here. That's going to help us solving some application problems along the way. If a is less than 0, our parabola will open down, and so we would have a maximum value here at the vertex. We've just been talking about max and min values as well. So here is the graph from the previous example. And if you look at this graph, remember this is f of x equals x minus 3 squared plus 2. And if we look at our formula for the standard form of a quadratic function, we can see right here that h equals 3, and we can see that k equals 2. So that this is just kind of some verification for this example, at least, that the vertex indeed can be found from the standard form of this quadratic function, and it is in fact the vertex is 3, 2 here. Okay, so let's go on. Let's rewrite a function in standard form, and you might want to practice with this a little bit with some other functions. Well, here we have f of x equals 2x squared minus 4x minus 1, and the first thing I want to do is I want to put some parentheses around the 2x squared minus 4x, because we're going to start by working with those two terms containing x so that we don't have a coefficient on the x squared. In other words, I want to pull out from those two terms the 2 so that I now have 2 times x squared minus 2x, and then we still have the minus 1 over here. Now, if you remember, we want to complete the square on x squared minus 2x. So the number I used to complete the square there, if you think about what we really want to do, is we want to write x squared minus 2x plus something as x minus something times x minus something. What would that something here be? Well, in this case, you can probably see that the two somethings here would need to add to negative 2. So we'd have x minus 1 times x minus 1. That would give us 1 right here. The general trick we use for finding the number that would go right here is to take the coefficient on x, in this case negative 2. If we take negative 2, divide it by 2, and then square it, that's going to give us our magic number of 1 here. And let's go ahead down here and let's put that plus 1 in the parentheses. So we want to add plus 1 here to complete the square. So what do I add over here? I can't just go adding numbers to one side of a function, right? So I need to compensate. So to the left here, we had 2 times 1 is what we added. We actually added 2 here. So if I subtract 2 to the right of the negative 1 here, I will have balanced out my right side of the function here. And so from this step, then, we can simply write our function as f of x equals 2 times x minus 1 squared minus 3. Okay, so let's go on with this function. We want to identify the vertex intercepts and graph this function. So recall, we just found that we can write this function in the form f of x equals 2 times x minus 1 squared minus 3. And using the vertex formula, remember a times x minus h squared plus k has the vertex of hk. Well, here we're going to see that the vertex is 1, negative 3. So we have a vertex of 1, negative 3. The x-intercepts here. So we've identified the vertex. To find the intercepts, we're going to start by finding the x-intercept. Remember, to find an x-intercept, we're going to set y equal to 0. So I'm going to go back to this original version of my function. It's usually easier for finding the x-intercepts. And if we do that, to find the x-intercepts, we set y, or f of x, equal to 0. So now I have 2x squared minus 4x minus 1 equals 0. Well, we want to solve for x here, so this doesn't factor. You can mess around with it a little bit if you want to, but we're going to go ahead and use the quadratic formula here to solve for x. So I have x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a down here. And we'll simplify, so we'll have x equals 4 plus or minus the square root of negative 4 squared is 16. 16 plus 8 gives me 24. So we have 4 plus or minus the square root of 24 over 4. We can think of the square root of 24 as the square root of 4 times 6 and pull out a 2 here. So now let's rewrite this as 4 plus or minus 2 square root of 6 over 4. And then if I factor a 2 out in the numerator and denominator, I can see that finally I'm going to have two different x-intercepts. Well, let's rewrite this, but we'd have 2 plus or minus square root of 6 over 2. And that would give me the two x-intercepts of 2 plus square root of 6 over 2, 0, and 2 minus square root of 6 over 2, 0. Remember that intercepts are points on the graph, so we want to write those as ordered pairs there. Then we're still in this same problem where we identify the vertex intercepts, and we've gotten the x-intercepts but not the y-intercept. So to find a y-intercept, we're going to set x equal to 0 here. So we'll have our y-intercept. To find the y value of that intercept, y equals 2 times 0 squared minus 4 times 0 minus 1, which simplifies to negative 1. Our y-intercept is the point on our graph, 0 and negative 1. And let's see, we have just about everything. Let's just rewrite the x-intercepts. 2 plus square root of 6 over 2, 0. And if you plug it in your calculator for plotting on our graph, that value of 2 plus square root of 6 over 2 is approximately 2.2. Then the other x-intercept, 2 minus square root of 6 over 2, 0. Using a calculator, we find it's approximately equal to negative 0.20. Well, let's get everything up, and then I'll start graphing. So the vertex is 1, negative 3. We found that earlier. The axis of symmetry, remember we look at the vertex for that x-coordinate of the vertex, or the first coordinate of the vertex, and then our axis of symmetry is going to be x equals 1. So let's put everything we have on here. The vertex is 1, negative 3. The axis of symmetry is x equals 1. Okay, so we have the vertex, the axis of symmetry. We have the y-intercept is 0, negative 1, and then we found our x-intercepts are approximately 2.20 and negative 0.20. And one other thing I can grab from this, I usually kind of like to have 5 points if possible. Notice the axis of symmetry is the vertical line about which our graph is symmetric. So if we go to the left by 1 unit to get the y-intercept of 0, negative 1, we can also, if we go to the left 1 unit to get 0, negative 1, we can also go to the right of the axis of symmetry to get the point 2, negative 1. And now I'll just try to connect these points in a smooth curve. Okay, something like so. And this is not the most beautiful graph, but I wanted to show you how I'd actually draw it by hand, because I know that you'll be needing to do that. One thing to make sure is that the vertex here, make sure your graph is looking curved there, that a curved vertex area. And I usually like to put arrows in on the end to indicate that the graph continues on forever. All right, so let's go on. And we're going to look at next the general form of a quadratic function, which is just kind of what we started with in the beginning. F of x equals ax squared plus bx plus c. And the vertex is negative b over 2a, f of negative b over 2a. So we don't have to put a function into vertex or standard form. We can actually use this little cheat formula of sorts. Where does this come from? Well, it would be possible that I could rewrite f of x here as f of x equals a times x minus h squared plus k. If you look in the textbook, I'm sure there is an example of this in the textbook. And so if we were able to, if we had the time to mess around with this function a little bit, we find that if we were able to write our function in this form, then h here would actually be negative b over 2a. That's where that comes from. And then the k you would also find was equivalent to f of negative b over 2a. Well, let's look at the example that we just had. F of x equals 2x squared minus 4x minus 1. And here the x-intercepts, so in general, we found the x-intercepts by taking negative b plus or minus the square root of b squared minus 4ac all over 2a. So what I want to show you is that this negative b over 2a that we have up here, A way to remember this is if you look at the quadratic formula and you just kind of circle this negative b over 2a, which in this case, for this particular problem, we simplified a little bit to find negative b over 2a would have been 4 over 4. That gives us the x-coordinate of our vertex. So here our vertex, the x-coordinate was 1. The x-coordinate was 1, 4 over 4. How would we get that y-coordinate then if we knew what the x-coordinate is? Well, it says find f of negative b over 2a. If we do that, we're going to find that f of 1 is equal to, here is our f of x. If we know that 1 is the x-coordinate of the vertex, to find the y-coordinate, we find f of 1, which would be 2 times 1 squared minus 4 times 1 minus 1, and that gives us 2 minus 4 minus 1, negative 3. So the negative 3 we can find by plugging the x-coordinate of 1 into our function here. And if we look on a graph, so recall in the graph we had the vertex right here of 1, negative 3. And if you look at the, actually I'm not totally sure why I included the graph here, but what you can note is that the 2 points on our x-axis here, these are the points of 1, what was that? Let me look back at my notes real quick. This was, what was 2 plus square root of 6 over 2. It would have been about 1, the x-coordinate here would have been 1 plus square root of 6 over 2. Now let me fix that. Sorry about that. Okay, so I was going to erase that and fix it here. So this would be 1 plus square root of 6 over 2, comma 0. This point right here would be 1 minus square root of 6 over 2, 0. So what's right in the middle of 1 minus square root of 6 over 2 and 1 plus square root of 6 over 2? Well, it's going to be 1. So that's another way that you can look at the quadratic formula and recognize we basically have 1 plus or minus square root of 24 over 4. Okay, so think about that, and I find that a good way to remember. I don't like to memorize a whole lot, so I kind of use whatever tricks I can find. So if we can remember the quadratic formula to give us our x-coordinate of the vertex here, it will be helpful, I think. Let's go on to doing an application problem here. The height h in feet of a model rocket above the ground t seconds after liftoff is given by h of t equals negative 5t squared plus 100t. For 0 less than or equal to t less than or equal to 20. So we're between 0 seconds and 20 seconds here. And if you check that out, that's going to be when the height is 0, when the model rocket's on the ground of sorts. When does the rocket reach its maximum height? What is its maximum height? So notice that we have a quadratic function here. And if we actually sketch this thing, if I sketched a graph of this, I would have t here in place of my x-axis. I would have h here in place of y. And the graph, it's going to look something like so. It opens down because a here is negative. And so this is a parabola and with a vertex. The vertex here would be t comma h. This would be our maximum value of h, and it would give us the time at which that occurs. So to find the vertex, we can use the formula negative b over 2a, h of negative b over 2a. So negative b over 2a is negative 100 over 2 times negative 5. That's b over 2a, and this is equal to negative 100 divided by negative 10 would give us positive 10. And that's going to give us the t value here. So the t value at the vertex is going to be 10 seconds. Okay, but we want to also find what is its maximum height. So we found when the maximum height occurs, what is its maximum height? Well, we're going to plug our value of 10 here back into our function h, and if we do that, we have h of 10 equals negative 5 times 10 squared plus 100 times 10. We'll simplify and get negative 500 plus 1,000, which we can add together to get 500. Okay, so this is the maximum height, and if we write that out in words, we would say the maximum height is 500 feet and occurs 10 seconds after liftoff. Then moving on to another application problem. This is one of the common types that we see frequently in homework problems and so forth. Tom has 32 feet of fencing. He plans to create a fenced-in area along one side of his house using the fencing. So let's just kind of sketch a picture over here on the side. Here's the house. Okay, and along that house, Tom wants to put some fencing, like so that he can have a fenced-in area. It doesn't really say, I guess, why he wants to do that, but he might have a garden there, or he might have a dog he wants to keep in a certain area or something. So he plans to create a fenced-in area along one side of his house using the fencing. What dimensions will maximize the area, and what is the maximum area? So I'm going to just, so the width here would be the same as the width here. We'll call that x, and then the length here we'll call y. Okay, so what is an objective function? Well, the objective function is what we're trying to find. What are we trying to find? The maximum area. So let's write what the area here would be in terms of x and y, and I would say it's going to be area equals x times y, according to our picture. Then we have a constraint. So if Tom had an infinite amount of fencing, he could do whatever he wanted to with that, right? He only has 32 feet of fencing. And that 32 feet of fencing has to go all the way around. So we'd have x plus y plus x again. And we could think of that as our constraint on the amount of area that we can fence is we're going to have 2x plus y has to be less than or equal to 32. Well, if we want to maximize, we'll just say that is equal to 32 here. If we solve for y, then y would equal negative 2x plus 32. Okay, well, I'm going to go back to my objective function here and apply the constraint for the y value here. And so if we do that, we're going to have a equals x times, we replace y with negative 2x plus 32, or a equals negative 2x squared plus 32x. Okay, so we have our area, and now we go back to what are we trying to find? Well, again, if we sketched a graph here, now let's see, I'll put a graph right here. So if we sketched a graph, kind of like in the last problem, what we'd have going on would be, we'd have a parabola, and if you look at our area function here, we have a parabola that opens down. It's going to go through the point 0, 0, right? If we set x equal to 0, then a would be equal to 0. So here is x, here is a. So we keep our x-axis as an x-axis, where in this case x is the width, and our a is the area. The vertex, the highest point on this graph, is going to occur at some point xa, and so we want to figure out what values of x and a would give us that vertex. Well, let's go back to, let's use negative b over 2a. We could also factor if we wanted to and put this into the standard form. Okay, so let's see. Let's go up here. So if I want to find the x-coordinate of the vertex, let's try negative little b over 2 times little a would be negative, here b is equal to 32, and a is equal to negative 2. So negative b over 2a, negative 32 over 2 times negative 2 would be the same as 32 over positive 4, or 8. So we found that the x-coordinate of the vertex is 8 feet. And then to find what the area would be at that time, we're going to have area. We're just going to plug in 8 for x here. So we're going to have the area that occurs at the vertex would be negative 2 times 8 squared plus 32 times 8, or negative 2 times 64 plus 32 times 8 is 256. So we have negative 128 plus 256. We end up with an area of 128 square feet, which we can write like this. Okay, we're asked for one other thing, what dimensions will maximize the area. We still need to find what y is. Well, notice we have a nice little equation for y here. So when x is equal to a, y would be equal to negative 2 times 8 plus 32. That would be negative 16 plus 32, or 16 feet. So what have we found? We have found the dimensions for the maximum area are 8 feet by 16 feet, and the maximum area is, so we'll say the dimensions are 8 feet by 16 feet for maximum area of, what did we find the maximum area was? I'm losing myself. 128 square feet. Okay, so there you go. And let's move on to our next problem, which is a try on your own. So go ahead and try this problem. For the profit function, p of x equals negative 1.4x squared plus 170x minus 150, where p is profit and x is number of items sold, find the vertex. Use your calculator and round to 2 decimal places. And then answer part B, what is the meaning of the vertex? Okay, let's go on to equations quadratic in form. So you may have seen these before, but because you'll run across them more frequently now, we want to review and make sure you're good with these. We're going to start by solving 4x to the 4th plus 9 equals 13x squared. And I'll begin by getting a 0 on one side. I subtract 13x squared from both sides to give me 4x squared minus 13x squared plus 9 equals 0. Okay, so quadratic in form means we want our highest power term to be something squared. Let's rewrite this as 4 times x squared squared minus 13 times x squared plus 9 equals 0. And now I can replace these x squared terms with a u to just help me factor or use a quadratic formula, whatever I need to do here. We want to just simplify a little bit before we go further. So I can write this as 4u squared minus 13u plus 9 equals 0. Of course, you don't have to do a u substitution. And in this case, it probably wouldn't be that difficult not to. But it's just something that we want to get used to using for future problems. Now we can factor this fairly easily into 4u minus 9 times u minus 1 equals 0. If you need to review factoring, that's a good thing to do at this point. You might want to go back to look at an old intermediate algebra textbook or something if you need some help with that. And setting each of these factors equal to 0 to solve for u, we end up with u equals 9/4 or u equals 1 as solutions. But notice we're not trying to solve for u here. We're trying to solve for x. So I go to the next step where I replace in u equals 9/4, I'm going to replace u with x squared so that I have x squared equals 9/4. And now remember, if x squared equals 9/4, x equals plus or minus the square root of 9/4, which gives us x equals plus or minus 3/2. So we have two solutions here. And then we're going to go on to where u equals 1. And again, I'm going to replace u with x squared. So I have x squared equals 1, from which we get x equals plus or minus 1. So altogether, we have 4 solutions here. And let me just circle all those. Okay, and we have it. Now another example, here we're going to solve y to the 1/3 plus y to the 1/6 minus 2 equals 0. Okay, well I'm going to start by rewriting this equation as y to the 1/6 squared in place of y to the 1/3 plus y to the 1/6 minus 2 equals 0. If you need to review also some rules of exponents, remember if we have y raised to the let's say y raised to the a, I started to write something else there, so let me fix that. If we have y raised to the a, then raised to the b, that's the same as y raised to the power a times b. And that's where you can verify here, y raised to the 1/6 squared is the same as y raised to the 1/6 times 2. 1/6 times 2 is 2/6 or 1/3. Okay, so we have y to the 1/6 squared plus y to the 1/6 minus 2 equals 0. And here we're going to let u equal y to the power of 1/6. So we can rewrite our equation as u squared plus u minus 2 equals 0. We'll factor to get u plus 2 times u minus 1 equals 0. I will set each of these factors equal to 0 and solve for u. So I have u equals -2 or u equals 1. But remember, we're solving for y this time, not u. And so in the first equation, u equals -2, I replace u with the y to the 1/6 that u is representing. And if y to the 1/6 equals -2, if you think of real numbers, there's no real number that I can take the 6th root of or any even root and get a negative number. So from y to the 1/6 equals -2, we will not get any solution. Let's go on though to u equals 1. And from u equals 1, I'm going to replace u with y to the 1/6. I have y to the 1/6 equals 1. And this should be okay. So what I'm going to do is I'm going to take y to the 1/6 raised to the 6th power equals 1 to the 6th power. I'm raising both sides of the equation to the 6th power. That gives me y equals 1. If I wanted to double check that y equals 1 works, I could go back to my original equation and plug in 1. I'd have 1 to the 1/3, which is 1, plus 1 to the 1/6, which is 1, minus 2 equals 0, and that does work. So it never hurts to check your answer. Okay, let's go on to try on your own number 2 for today. Solve the equation x to the 6th plus 7x cubed equals 8. And let me know if you have any questions about anything.